Hi, everybody. Good morning. Welcome to our 10 a.m. stream today. My dog is attention seeking this morning. Hi, guys. There's like some names I haven't seen in a while. Hello. I'm happy you got to be here. Sort of. Not here, but the social distancing version of here. Winnie, can you play with that somewhere else, please? Alrighty, so today, I really like this lesson. Because for one, it's something that you probably have done several times in your math careers so far. And also we get to do some visual proofs, which is like one of the coolest things that I don't know why. I just really like it. You might disagree with me, but anyhow, so we're gonna just sort of review the formulas for some of the basic shapes, and then we're gonna add a couple of shapes you probably haven't seen the formulas for. And more importantly, we're going to talk about why those formulas work, using the knowledge that you already have, which should be fun, hopefully. So, first, I don't know if this is said very much, but and I think it's important just to sort of preface any squares fit into like little squares fit into a shape. So for like a rectangle, the base and the height, we usually label it like base and height with the base on the bottom. And so the base is essentially how long it is on the bottom, and the height is how tall it is. And when you multiply those two numbers together, what you're doing is you're counting how many of these like squares fit into this entire rectangle. I can't do it perfectly, but so that's what we're doing when we're finding an area, is we're trying to figure out how much like square footage, kind of, except for it's not always in feet. How many square units fit into the interior of that shape? And so clearly it's a lot more than just the base and height, which is why this works. When we multiply base and height together, we get how many squares fit in there. Each of these squares counts as one unit of area, and we total that up, and that's the area, which is why area has the units squared as its units. It's squared because it's little square versions of that. It's not just a length, it's an area, it's a square. Yeah, so a rectangle's area formula is really basic, and it's kind of the most basic principle of finding area, is you're multiplying that bottom length by the height length to figure out how many of those squares fit in it. And it's really nice when it's a rectangle because it's always whole squares that fit in there. For a triangle, it's not always whole squares. You're going to end up with like half of squares happening. This is where it becomes useful to have formulas so that we don't have to like actually count squares, which we never really have to do. But the formula for a triangle is the base, which again is the length along the bottom of the triangle, times the height, which is always the maximum height in the shape. And this works for any kind of triangle, so like right triangles as well. Right triangles, though, the height ends up being one of the legs of the triangle, and the base is the other leg. We can actually talk about why this formula works for a triangle in just a second when we talk about a parallelogram. So we're going to talk about a parallelogram first, and we'll do the visual proof for that one, and then we'll come back and talk about why the formula for a triangle is base times height divided by 2. Just for now, note that it's essentially the area formula for a rectangle, but in half. Just remember that. So now we're going to talk about a parallelogram. So parallelogram, to find the area of a parallelogram, you need two things. Height, again, and notice that this height is not, it's not the slanted piece of the parallelogram, it's how tall it is, just kind of like the triangle. The triangle's like slant height is not going to be helpful in the formula. You need the actual like physical height of that shape. And then you also need the base, which is just the length along the base. And so I think I'm going to show you the visual proof first before I give you the formula, because I think it's more interesting to develop the formula instead of just have it given to you. So we're going to start the visual proof by just drawing a parallelogram here, and with its base and its height. And I'm actually gonna color this little triangle that I just created with the height pink, because we're gonna need that as sort of a separate piece in a second. So that's what I'm doing. I'm just labeling it differently. And here's what we're gonna do. We're gonna here's our parallelogram again. We're gonna take that triangle and move it over here. And that means we no longer have this piece. And that is why I was coloring it pink, so we can kind of tell where it went. And here's our height still, and here's our base. And look what we just created. That is just a rectangle. If you chop off the little triangle on the front part of the parallelogram and move it to the other side, it just becomes a perfect rectangle. And so the formula for the area of a parallelogram is the same as the formula for a rectangle, because it's essentially just moving a piece of a rectangle over a little bit. And so the area formula is the same. So it gives us just this nice rectangle shape, which is why the area formula for a parallelogram is just base times height. And now that we've talked about a parallelogram, a triangle, the formula for a triangle makes a little bit more sense. Every triangle, no matter what triangle you're looking at, can, if you duplicate it, copy paste that same exact triangle and move it around, you will actually be able to make a parallelogram with two of those triangles, no matter what triangle. You should actually try that. That's my challenge for you. Cut out any kind of triangle out of a piece of paper and then copy it onto, make another one and see if you can fit it together into a parallelogram. Because no matter what triangle you're looking at, it will actually work. Two triangles always make a parallelogram, which is why the formula for a triangle is half of what the parallelogram formula is. It's base times height, but in half. So I'm just going to show you in a quick example. I don't actually care if you write this down because it's not super important. It's just kind of for funsies. If I have that triangle, it's not quite a right triangle. Sometimes I have to think about how to fit these things together. Oh yeah. And then I duplicate it and turn it upside down. Do you see that? I've just made a duplicated same triangle right here. It's just turned upside down. That made a parallelogram. It's kind of a stretch parallelogram. Yikes, that's a hard one to say. But it's still a parallelogram. And if you were to find the area of that whole shape, the parallelogram, it would be base times height. But just one of those triangles is half of the base times height. This is a parallelogram. There you go. And And let's talk about a trapezoid. So, just as a note, the trapezoid formula that I'm giving you works for every trapezoid. This isn't, remember from our first lesson, we talked about isosceles trapezoids, how isosceles has the same, um, it has two parallel lines and then the other two sides are the same length. So essentially, a lot of other things happen, like it has the same angles on the bottom and those two are the same and the same height. Anyway, so this works for every trapezoid, not just isosceles trapezoids. So it could be a really funky trapezoid with one side really long and one side like not even slanted at all. So we're gonna do the visual proof for this one. This one is the one that I like. There's actually several different visual proofs for the trapezoid, but this is the one that I like the most. So I'm sorry if you don't like it, but we're gonna start with just a trapezoid. Oops, wrong color. And I would recommend maybe drawing small. This one we need more room than we did last time. So here's my height. Here's my We're gonna need a base 1 and a base 2. So sorry if that's too small for you to see my 1 and 2. I can't like zoom in very much, but you have the height and then you have the upper base. I don't know why we don't just call that like the top or something, but whatever. Base 1 and base 2. And then it's kind of like what we did just now with the triangles, we're gonna duplicate the same trapezoid. So I'm just gonna indicate that what I'm doing by multiplying by 2 like that. And so here we have my one trapezoid, and then I'm just going to, I'm lucky because I'm using technology and I can literally copy and paste. Here's my other trapezoid. Again, it has a height, a first base, and a second base. And then I'm just gonna highlight this one like pink or whatever. It doesn't have to be pink. That's the highlighter I have ready. Just so I can tell them apart when I keep going. So now I have two of the same trapezoid. And what I'm actually gonna do is, and this is kind of funky, is I'm going to flip the pink trapezoid upside down and then try to like it fits in with its other duplicate really nicely. So I'll just show you what that looks like. Here's our original trapezoid. And then the other trapezoid can actually fit the first one perfectly, just like that. And now we have, since we flipped it upside down, the base 1 of that trapezoid is actually on the bottom. Here's base 1, here's base 2. The reason for all of this, just to update any of you who came in after I started, the point of all of this is to develop a formula for the area of a trapezoid. I don't expect you to be able to replicate this, but I think it's cool to know where the formulas came from. So we sort of rotated that one upside down and fit it into its counterpart. So now what we have magically is actually a very long parallelogram. That guy just keeps coming back. Do you notice that we now have a shape that looks like a long parallelogram? And the area formula for the parallelogram is just base times height. So we're going to use the measurements we were already indicating, the base 1 and base 2. So on the top here, notice that we have, wait, let me get my pointer. There it is. We have base 1 and base 2. So the total distance along the top or bottom of the trapezoid is base 2 plus base 1. That's the whole thing. So on the bottom of our trapezoid, it's base 1 plus base 2, because that's how long that whole thing is, according to our original measurements. And then the height is the same, it's just the height. And so the area of this whole parallelogram, the giant one that we just made, yes. So you would just multiply, because the area formula for a parallelogram, you would just, oh my gosh, I can't talk. The longer I don't talk to people, the more awkward it is to talk at all. My brain just like forgets how to do it. Anyway, so because it's a parallelogram, you need the base and the height, and we just figured out that the base is base 1 plus base 2 in this specific parallelogram, and then the height is just height. So we have base 1 plus base 2, and we're multiplying that by the height because that's what the whole parallelogram is. But remember how we duplicated it? We don't need the whole thing. We just needed one of those trapezoids, not both of them. And this is like, if this works for any trapezoid, but we're just using like a very general case. We just wanted one of them, and we doubled it at the beginning to help us figure out the formula. So we need to do the reverse of that, which ends up being to divide by 2. So you've probably seen that formula before. You've probably seen height times base 1 plus base 2 over 2. Hopefully that looks familiar. I'm pretty sure you would have seen that at some point in your life. But that's why. You essentially can like figure out that formula if you're ever to forget. If you're like me, which I don't know how many of you are, but sometimes I have to think of this visual proof when I've forgotten the formula, because remembering formulas is just memorization. And math is not memorization, it's sometimes figuring stuff out. Most of the time, you can figure it out. And that's what I like about math. So that's the formula. Height times base 1 plus base 2 divided by 2. Don't forget the parentheses, that's important. That's the height, and then the top is base 1 and the bottom is base 2. And again, there are other ways of developing that formula if you are bored, which I'm sure you're not. If you're bored, try to see if you can find another visual proof and email it to me, because that would make my day. Okay, so that's the trapezoid formula. We're going to move on to kites. This visual proof is actually really fun too. Like I said, I like these and I don't know how to explain it. Here's my kite. I'm going to turn it on its side because it's going to make more sense in a second. And the two measurements for this kite, and actually I'll draw them on here too. The two measurements we're going to have is this, we're going to call it Q and P. I don't know why they use Q and P on a kite, but they do. So it's just that vertical height and then the horizontal breadth, depth, width. That's what I'm looking for, width. So on our sideways one, this is P, this is Q, and the other one's P. Q and P. Hang on, let me zoom in. And then what I'm gonna do is highlight, yikes, it's too big. The highlighter doesn't go any smaller. Oh, yes, it does. Brilliant. Okay, I'm just gonna highlight one of these pieces pink and another one a different color. It doesn't matter what color you're using, but and we're trying to make this into a shape that we already are familiar with, and so what we're gonna do is we're gonna move this one and fill in that space, and move this one and fill in that space, because as you might notice, if we do that, it turns into a very familiar shape. So we're left with just the top half of our kite, and then we moved the pink section up there and the blue section up here. Oops. Look at that. Never knew, huh? And even though it doesn't look like super nice on my drawing, that is a rectangle. And the only tricky part of this is that, so the whole length is Q. That one's the easy one. The whole length is Q. But this, we need this height. What would normally be the height in in a rectangle. And notice that this, when we were here before, let me get my pointer, when we're over here, this whole length was P. And this is only half of that value. The whole length was P, and we moved half of it to a different place. And so the total height is actually P, half of P, P over 2. So as you might imagine, the area formula for this, for a kite, this shape, is Q times P over 2. Or if it's nicer to write it with P and Q both on the top. So it's P times Q divided by 2 is the area formula. Because we can move pieces around and just make it into a rectangle with P over 2 here and Q on the bottom. So there you go. Easy peasy. P times Q divided by 2. So you just need that total vertical distance and the total width of the kite. I am not sure what you mean, Gabe, about find the area of a trapezoid by having the area of it as if it was a hexagon. Oh, I see what you're saying. Hexagons are harder to find the area for that. So you would have to be able to find the area of the hexagon, which I guess in this case would end up being, no matter what you did, it would end up being the formula for a trapezoid, but you should try that. See if you can figure it out. This next part actually might help with that. Turning the page. Here is a pentagon. Our lovely pentagon. And the measurements for this pentagon, you might not actually see this in your homework. Just, I don't know. I couldn't find any problems like this, but on this pentagon, we're going to be using a couple of different measurements. I'm splitting it up into triangles that meet in the middle. That might give you a hint as to what our vertical or our visual proof will be. But we're using the height of one of those triangles and then one of the side lengths. We're going to just call it S. Yeah, it would be about the equivalent, Nick. Like, no matter what you did, you would end up at the same formula as long as you did it right, but it would be interesting to see if you could get at it from the perspective of a hexagon, but I don't know. Anyway, sorry. Okay, so we're gonna use the side length. Man, I hate using S as a variable because it looks like a 5. I'm gonna use B instead. I'm gonna change that, sorry. So as you might imagine, our visual proof for this one is gonna involve finding the area of a bunch of triangles, all of the same triangles. Remember that this is a regular pentagon, so that means that all of the sides are the same, which is really hard to draw accurately, but that's gonna have to work. And this formula would not work for something that's not a regular pentagon. If it's a different kind of pentagon, it's not gonna work because your triangles will not always be the same. So I'm just gonna focus in on this single triangle in the pentagon. I can't draw it here. Okay, here's my triangle. Actually, I'm gonna highlight it so we can tell what we're doing. So it is a triangle with just a base and a height, where our labeling is actually the same as a normal triangle, and there's 5 of them. which means that the formula for this regular pentagon will be the formula for a triangle is just base times height, but halved divided by 2. So essentially we have base times height divided by 2 for each of those triangles. So we would multiply that whole thing by 5 because there are 5 of those triangles. So yeah, you can write that a bunch of different ways. I don't care as long as it's equivalent. But that's the area formula for a regular pentagon. If you have that, if you have those measurements, then it's super easy. I'm gonna write it like this: 5 halves base times height. Yikes. Because I don't know why, but that looks better to me. It's actually the same. I'm just moving stuff around in that formula, but it's equivalent. So then it's asking us to think about what would change for a hexagon or an octagon. So remember that we just found the area of a bunch of triangles, all of the same triangles, and there were 5 of them in a pentagon. And so you might imagine how many might there be in a hexagon? 6, right? Because there are 6 sides of a hexagon, and each of those sides would make a triangle with like the center middle piece. I don't know how to say that. Each of those would make a triangle. And so there would be 6 triangles instead of 5 triangles. And the only thing that would change actually in our formula, hang on, I'll write it up here. So for a hexagon, I don't know if I can draw a hexagon today. Hexagon, close enough. So a hexagon would have 6 of those triangles. So the only thing that would change is we would have our base times height over 2 for each of those triangles, but then we would be multiplying by 6 instead of 5. And for an octagon, there would be 8 of those triangles, so it would be base times height over 2 times 8 instead of times 6. So you can adapt this formula with just those number of triangles to sort of find the area of any regular n-gon. Or that's just a word to mean like any number of sides, shapes. As long as it's regular, this will work. So for a hexagon, let me just answer the question down here where it asks it. A hexagon would be 6 halves times base times height, and an octagon would be 8 halves base times height. Again, I just moved numbers around because that way looks nicer to me. But yeah. And the last super important area formula is the area formula for a circle. We have actually already learned this, but we did not do a visual proof for it. Some of you did actually on your performance task. So if you already know this, then you're like, great, that's awesome. But I'm just gonna show you guys the visual proof for the area of a circle and why it works. I don't know why. I didn't see this until college, and it was like, wow, you can figure this stuff out. It's really cool to be able to like not have to remember formulas because math is figure outable. That's the word. I just made it up, but it's a good one. Okay, so our visual proof, we're gonna start with a circle, and bear with me because I know this is like weird. But what we're gonna do is just split this circle up into, I don't know, 8 pieces. It actually doesn't matter, and you'll see why. But we're splitting up into 8 pieces, and I'm going to highlight every other piece one color, and every other piece a different color. So then you have this cool pinwheel. And we're gonna sort of separate, so each of those pieces is like a pizza slice, right? It has like a round edge, and we call it an arc because we are mathematicians. Actually, no, it's a sector, isn't it? Yeah, sector area. That's what we learned. So it's a sector area. It's a sector. So we have a bunch of these sectors out of our circle, and we're just gonna rearrange them, and we're gonna rearrange them like this. Wait, that's too big. We're going to try to make it the same size as our actual circle sectors. Okay. This sometimes takes a lot of art skills. Okay, we're just stacking them like that. And I will highlight just to like indicate, just to make it clearer what I'm actually doing. I just took half of the, oh, I don't have enough, huh? Here's my last one. There you go. I just took half of the sectors and I put them upside down and the other half right side up. And then sort of meshed them. So the cool thing is, the smaller pieces of a circle you get, you can arrange them closer and closer to a rectangle. Like you can't really, like at this point, there are not that many of our sectors, so that does not look like a rectangle. But I'm going to draw another really quickly where we split it up into a lot more sectors, and you'll see sort of what happens with this shape when we mesh them. I think I'm splitting into 16 pieces. I just doubled the amount of pieces we split it up into. And so we can take all of those sectors, and surprisingly it fits very close into what would be a rectangle. And the smaller your pieces get, the closer this shape becomes to a rectangle. And if I don't know if we actually have enough in that one, but it doesn't matter because what you're seeing is that this slowly becomes a rectangle the smaller the pieces get. And we know the area formula for a rectangle. Here's the tricky part, though. We need to figure out the measurements in a circle. Base times height is not going to help us here unless we know what the base of that rectangle is and what the height of that rectangle is. So, you might notice that each of these sectors, the height of that is just a radius. The height of our rectangle is just the radius. And then the hardest part is figuring out the length. Like how long is this rectangle? And here's the cool part. So notice that we meshed our sectors, like half is on the bottom and half is on the top. And if you were to measure around each of those little like arcs, each of those bumps on the top and on the bottom, you would end up with the whole circumference of the circle, right? If you measure all of those arcs that we had, both on the top and on the bottom, you would end up with the whole circumference because that's what you started with. And it turns out that you actually halved that circumference, so half of it is on the top and half of the circumference is on the bottom. And so the length of this rectangle is exactly half of the circumference of the circle. So the circumference, remember, is pi times 2 times the radius. Or pi times the diameter, but we're going to use radius. So if we half that, half of the circumference is just pi times the radius because we have a 2 in there, and if we were to divide it by 2, it just ends up being, the 2's cancel out, so you end up with just pi times r. So the length of this rectangle is pi times the radius. So here's the magic. The height of the rectangle is the radius, and the length is pi times the radius. And so the area of the whole, let me move this. Here's the height. So the area of the whole rectangle that we just created is radius times pi times the radius, because it's base times height for a rectangle. And you end up with two r's multiplied together, so that's like r squared times pi. Does that look familiar? Hopefully. The area of a circle is pi times the radius squared. Anyway, I think that's super fun and cool. Yeah, so that's where the area of a circle comes from. That's why it works. And I think it's fun. So here's the only thing that you need for that is actually the radius on a circle. So there's a bunch of problems, and I would encourage you to perhaps pause me and try doing these problems by yourself. I'm gonna keep going because you can pause me, and that's cool. The most important part of this is I want you to be able to, at the end of this lesson, be able to sort of piece together compound shape areas, which comes on the next page. We're going to do a couple of problems on the next page with compound area. So I'm going to sort of blow through these really quickly because I want to get to those ones. Because these are just shapes, nice shapes. The first one's a circle. And we're going to say this is the radius because I want to use nice numbers. So the area is pi times 5 squared because it's pi times the radius squared. So calculator. Oh, I lost my calculator. I'll be right back. Here it is. Okay. So pi times 5 to the second power 78.54. If that's wrong, please tell me. Doesn't give us units, so it's just units squared. That's the area of that circle. The next one looks like a parallelogram to me. So the tricky part about problems from like state testing, like the ACT and stuff, a lot of times what they do is give you too much information. So it's sometimes the hardest part of a problem is figuring out what information you actually need and what you don't. So notice that on number 2, it gives us the slant height. It gives us that the length of that piece is 11.3. We don't need that information. We just need the height and the base. So like this is something you can completely disregard and still get the problem perfectly right. So that's just something to think about. That happens sometimes, especially on state testing, because they're trying to trick you, kind of. So the height is 7.8 and the base is 14.1. The formula for a parallelogram is just base times height. So we're just multiplying those two numbers together, and that gives me 109.98 units squared. Yep. And last we have a kite. Notice again, we're given too much information. All we need for the area of a kite is the P and the Q values, which are like I've never like done kites. So I don't know what the word for that, like the cross pieces of a kite are, but that's all you need is the length of the vertical length and the horizontal length of the kite. You do not need that 15.2. And if you need the area formula for a kite, flip back to it really quickly. But it's just P times Q divided by 2. So we're just doing 11.9 times 19.9, but divided by 2. Gives me, oh, it's 11.8. Sorry. That gave me 117.41. units squared is the area of that kite. So, that's good. But let's do exciting stuff now. Let's put a bunch of different shapes together. I like that stuff. So, these are called compound shapes. I think that I've probably explained that because on some of your performance tasks, you've been asked to find compound shapes and find the area of compound shapes. So essentially, hopefully this is not like super brand new, but compound shapes are just shapes that are stuck together. They're a bunch of different shapes stuck together, and the way that you find the area of them is finding all of their pieces and adding them together. So this first ice cream cone type shape, hopefully you can see there that the area of the whole shape is going to be the area of half of a circle plus the area of the upside down triangle. I like to do that at the very beginning of my problems just to indicate to myself what I'm doing to keep track of like where my formulas are. Because as soon as you start plugging numbers into formulas, it gets really convoluted and it's hard to like keep track of where which shape is which and where you're adding and where you're multiplying. So I like to keep track of it like this. I like to sort of keep it in sections. So I'm going to do the area formula for a circle and the area formula for a triangle, and I know that because I have it written down, and it's going to be just underneath so I can keep track of them. That's something that works for me. So I know the area formula for a circle is pi times the radius squared, but this is not a whole circle, it's half of a circle. So you can use possibly 180 over 360, like you could do sector area on this one. It will give you the same answer, but I'm just going to divide by 2. So I'm going to do pi times the radius squared, but I'm going to half it because it's half of a circle. And then a triangle is just base times height over 2. So now that I have my formulas, I can plug in the numbers from my actual problem. So something to notice is that this 26 is not a radius, and I need the radius. 26 is all the way across here, so the radius is going to have to be half of that because this goes all the way across. Probably the thing that's going to happen a lot is making really small mistakes on these problems, like using 26 as the radius instead of 13. Just be careful about that. Usually these aren't hard except for there's a lot of area for little mistakes like that. So I'm going to use pi times 13 squared divided by 2 plus, and then the base of the triangle is 26 and the height is 22, and we're dividing it by 2. At this point you can type it into a calculator. I'm going to do that because I ran out of room. So I'm going to type it into a calculator just the way that it is. Be careful to put parentheses where you might need them, because sometimes calculators don't understand what we're saying unless we put parentheses. And then we have 26 times 22 divided by 2. Okay. Area for little mistakes. Yes, I appreciate puns. I did not even mean that one. Okay, so I got 551.46 or 0.5. I'm just going to round to the first decimal place. Units squared, and that's the area of that whole compound shape. 551.5. And so something that you guys, if you have done some of those performance tasks, I've noted that a lot of logos are compound shapes. Like that, they look good and they look perfect because they're made out of like these really specific and understandable shapes. So people like to make logos out of them anyway. So these you will see actually in the world, and they're fun to make, kind of. So we're gonna do this little cloud, I guess, shape. And I'm seeing that we have a half of a circle this way, but also a half of a circle this way. That's these two shapes, this one and this one. And they have the same radius and the same diameter, which means that I'm just gonna pretend that they're one circle, because I don't want to have two halves of a circle and add them together. That doesn't make sense, because I could just do a whole circle. So here's my whole circle. And then I have a top half of a circle. That one is gonna be a half one because we don't have another part to make it a whole. And then a rectangle in the middle of it. So I'm not gonna write my formulas because I am gonna run out of room again. So I'm just gonna skip straight to this part where we're putting the numbers in. Again, for these two pink circles, that's the 21.3 is the diameter. We want the radius. So I'm just gonna really quickly divide 21.3 by 2 to figure out what the radius is. I got 10.65 squared. So these are my pink circle formulas, and I'm not dividing it by 2 because it's a whole circle. And then I'm gonna find the top circle. 31 is the diameter, so I'm gonna half it, which gives me 15.5. So pi times 15.5 squared. And that one does need to be halved because it's half of a circle. I don't have a whole one. And then the rectangle is just the height times the base. So 31 times 21.3. Do not have enough space in this paper. I apologize. I should zoom in more, huh? Okay, and then at this point you can type it into a calculator. I'm gonna do the calculations like separately because sometimes that helps my brain keep track of what I'm doing. Again, please tell me if these are wrong. And then you add all those pieces together, and I got 1,771.3 units squared. Here, maybe I'll color code this a little bit more because Miss John likes to color code things. Okay. I know this next one looks really complicated, but actually if you were to sort of just kind of like what we were doing in our visual proofs, move stuff around so it's a simpler shape, it actually isn't that bad. What I'm going to do is this top triangle and this bottom triangle have the same base. Both have a base of 20, and they also have the same height. Both have the height of 39. So what I'm going to do is pretend that they are, wow, I have like no room on this one. I'm going to do it up here. I'm going to pretend that they're one big triangle halved in the middle like this. Here's my two triangles. And then the other shape is just a parallelogram with a height of 18 and a base of 40 because it's 20 plus 20. So to keep going on our area formula, our triangle will be base times height divided by 2. So on that big triangle that we just created, that compound triangle, I guess, the base is 40 because we combined both of those triangles to be one, and both halves of it had 20 as the base. So it's essentially like we moved that pink triangle up here, and now the base is all of this, 40. That's what we did. So the base is 40 and the height is 39. It's possible to see, I know, but there you go. So our formula, because the formula for a triangle was base times height divided by 2, we're going to do 39 times 40 divided by 2. and the area formula for a parallelogram, and I'm going to run out of room again, but parallelograms are just height times base, and the height of that parallelogram is 18, and the base is 40. So we have 18 times 40, and that's it. We have our giant amalgam triangle. Okay, what did you get, Nick? I'll double check. Might work on that in a second. 39 times 40 divided by 2 plus 18 times 40. Just adding some parentheses because I'm scared it's doing it wrong. Okay. And that comes out to 1500 exactly, I think. Okay, Nick says I got this wrong, so I'm gonna double check. Let me just type it in because I didn't actually type it in. I was just using my work from before, which is scary because who knows if I did it right. Plus pi times 15.5 divided by 2 plus 31 times 21.3. Oh, yep, you're right. I don't know which one I got wrong, but I'm gonna just erase these middle pieces because I'm scared that those are wrong too. See? Room for mistakes, right? I do it plenty. That's why I don't super care what your grade on your math base is. Okay. That's what you got, right? Yeah, 0.1, 0.01. Yeah. That's better. Okay, 1394.01 and then 1500 units squared. Okay, and we're going to do one more. So even though this looks really scary, this is not a very nice shape, but well, it's fine. It's not that bad. So what we have is this weird like rectangle with a circle cut out of it shape. And then we also have half of a circle. And we have a sideways triangle like that. Those are sort of the three parts. And the cool thing is that these two things like fit into each other like puzzle pieces. Obviously that's not going to happen all the time, but on this one, the diameter of the circle, the half of the circle, is the same as the base of the rectangle. So there's no way it doesn't fit, essentially. So we're going to combine those into what is just a rectangle. Those two pieces, which makes our lives very easy. And then we have this triangle shape. So, so that rectangle piece that we just made has a base of 56 and a height of 39. So, we can do that math. 56 times 39 plus, and then the triangle, so the base, be careful to figure out where the base is. Here, the base of the triangle is right here, but that's the same as this other side of the rectangle. So this piece is also going to be 39 because that piece is. So the base of the triangle is 39, and the height is 34. So we have 39 times 34 divided by 2. Area formula for a triangle, base times height divided by 2. And now we can just do calculator work. 56 times 39 plus 39 times 34 divided by 2. Double check me on that one too, but I think it's 2847 units squared. Exactly. use parentheses. Yep, got the same thing. So I think that's it. Any questions? I know that I went through that fast. Remember that you are allowed to pause me and also ask questions. So you have a homework assignment today. Well, there's one that's due today. Unit 9-2 is due today at 5, and 9-3, which is assigned today, will be due on Thursday, so just be looking for that. I will have a study session or two today. I just have started posting the link on Google Hangouts so that anybody can join whenever. I'm just gonna put when I'm gonna get off so that you know if you're like too late or not to join. So anyway, join me. I'm going crazy by myself, so I like to talk to people instead of just to a camera. So entertain me. I appreciate it. Also, I can help you with your homework. Bonus points. What else? I don't think there's anything else. Just be careful on this. I know that it's like really easy to make a mistake. I do it all the time. Yeah, make sure your calculator work has parentheses and you don't use the diameter as your radius in a circle, that kind of thing. I think that's all. Any questions? I'm gonna wait for a second in case you guys do, and I think that's all. Winnie, come here. Come see me. Come here. Come here. Good girl. Yeah, number 2. There's number 2. I will probably do the study session at I have to call somebody. So let's do it at like 11:30. That's probably when I'll send out the link. I'll probably do it 11:30 to 12:30. I might do one later. I don't know. Sometimes I forget, but probably 11:30. If you want me to do a study session though at a certain time, like I don't have as much scheduling to do as you guys do because I am only doing this. I mean, this is like you guys are my job. So if you are free like at a certain time or you need help at a certain time, just like message me on Google Hangouts or email me or whatever. I'm happy to accommodate because I know that like I do it at about the same time range every day, and so if you're like not available for that time range, it's a bummer. So let me know. And I think yeah, I think that's good. Okay, so I'll hop off. I will send out a link today for the study session, and let me know if you have any questions. But bye. Have a good rest of your day.